All right, in this section, we're going to take a look here at 6.1. As our first section in Chapter 6, it's important for us to kind of quickly recap what we've been doing in Calc 2 thus far and why exactly we're here in Chapter 6 and what's our goal in this chapter. Well, remember that we started in our first chapter talking about how we can repurpose an integral to do a whole bunch of different things. We found volumes and areas and surface areas and arc lengths and a whole bunch of different things. But in the second exam, we took a look at how do I evaluate those complicated integrals that begin to come up. And what we found in the process of that second exam was that there were several integrals, in fact, an infinite family of integrals that did not have easy antiderivatives. These were integrals like e to the negative x squared we had kind of talked about. So we started pursuing Chapter 5, which was apparently an effort to develop a final integration technique that might be able to help us with complicated functions like e to the power of negative x squared. So in Chapter 6, what we're going to be able to do here is start to figure out how in the world does that material from Chapter 5 actually help me? Because you might have gotten all the way through Chapter 5 not really understanding why any of this or how any of this relates to integrating really difficult functions. So as I state here at the top, Chapter 5 was concerned with the development of ideas surrounding the convergence and divergence of a lot of different types of series. And now we determine how is it relevant. So in order to do that, we're going to quickly do a recap of a Calc 1 topic that's very important for our purposes here. Back in Calc 1, you probably would have talked about the idea of what we call a local linear approximation. The idea was as follows. Sometimes there are really difficult functions that are in the world. Maybe that difficult function is this one, y equals f of x. And maybe there's a value out in the world that I would like to go ahead and plug in. Okay? Maybe I want to plug that value into this function. Maybe it's something like I want to take the square root of pi, and it's like, I don't know how to do that. That's tough to determine in my head. I mean, if I believe what calculators tell me, then I guess I can discover the value, but how would I program a calculator to get me that answer? What would I do? So if I want to plug in that really difficult x, then I know I'm going to get some y back, but I don't know how to do it. And so the idea in Calc 1 was to say, well, let's use the idea of tangent lines to our benefit. We'll say that instead of actually going ahead and plugging in that mystery difficult value, we'll plug in this value of a into the function. And hopefully that's an easy value to plug in. Maybe like square root of 4. That's not bad. I can do that in my head. And that will give me a y coordinate back that's called f of a, right? It's just whatever the y spits back. And if we build a tangent line there, we'll notice something. We'll then have two equations. We'll have the hard equation, and we'll have this other equation over here that I've called p of x. And that's the equation of our line. It's an easy equation. It's just, something like a y or an mx plus b formula. And so that should actually be an equation that would be really easy to handle when I wanted to plug in this difficult question mark value into that p of x function. What I'll notice is that when I plug that difficult value into the line, I won't get exactly the black dot up here that I was looking for. I won't find exactly that y coordinate, but I'll definitely find something that's pretty darn close by. And you'll notice that the closer I move this question mark to a, the smaller the gap between that black dot and that blue dot become. So what we wanted to try to understand is how we could use this idea and how we could construct this equation of a tangent line. So notice that this is ultimately the construction that we would go through to get the equation of this tangent line. So I'll say to get the equation of the tangent line at x equals a, we compute, and notice I'm just going to start by setting up point slope form. If I know a point that's already on my line, and I do, it's that a f of a, I could start by writing y minus my y coordinate should be equal to, I'll leave a blank for slope, and then I should have x minus x coordinate. Now in Calc 1, we talked about how I would actually determine the slope of a tangent line at any point on a curve. And the way I would do that is with a nice derivative. So if I wanted to, I could go ahead and see that y would then be equal to f prime of a times x minus a plus f of a, if I added that f of a to the other side. And the only thing that I've done here is I've just said, I'm going to call y p of x. I'm not going to change the formula at all. I'm just going to go ahead and change the way I label it. Okay, so this is the way that I could go ahead and actually work with this. And again, what we'll notice is that for values that are really, really close to A, if I plug in question mark points that are close to A, again, the blue dot that I get back from the P of X formula will be almost the same as what I get back from the F of X formula. And so this allows me to do a lot of cool approximations. Now, I'm going to take a look here at example 1 to give an idea of how something like this could actually work. So take a look here really quickly. I'll start by drawing a picture. I want to find a local linear approximation of f of x equals e to the x at x equals 0. So in a picture, I'm going to go ahead over here and I can just quickly sketch out my graph of e to the x. I know it looks and it goes like this. Okay, so this is y, or f of x equals e to the x. Okay, and I want to go ahead and create a tangent line that comes right off of this curve at 0. Okay, so maybe that tangent line looks something like this, and I'm going to call this my p of x, and I'm interested in finding that formula for p of x. Okay, so this isn't too terribly difficult to do. Again, I'll know exactly how to construct this because I know how to construct the equation of a tangent line. I just need a point and I need a slope. So it's pretty easy to see here that if I'm interested in grabbing a point and I'm interested in grabbing a slope, these values are easy to find. I see that my point on the line is that black point right on the y-axis. It's got x-coordinate 0 and its y-coordinate, well, its y-coordinate has got to be 1, right? Because if I plug 0 into e to the x, I get back 1. I can then also see that in order to find the slope, I would need to calculate the derivative. So the derivative of my function is going to be, well, e to the x. That's easy. And so my slope, m, is just going to be that derivative evaluated at 0, which of course is just the number 1. So if I have a point and a slope, I can build the equation of my tangent line. I'll say here, the linear approximation is, and I'll just call it p of x. So I'm going to do p of x minus my y-coordinate is equal to my slope times x minus the x-coordinate. I did everything that I did up here. I just haven't added the y value over to the other side. Of course, if I do that, I end up with the formula x plus 1. So this right here represents that equation of that tangent line. And again, there's value in this equation that we've been able to form right here. So we know that for values close to x equals 0, f of x is roughly equal to p of x. Like, take a look at the picture even, you can see it. What would happen if I maybe plugged in 1/1,000,000th, right? If I plugged in 1/1,000,000th and I go up to the picture, can you even visually see a difference right now between p of x and f of x? No, I mean, like on a small enough window, right? Like if I only looked maybe from, like this point right here over to this point right here, if I kind of covered up the rest of the screen, I could barely tell any difference at all between these two functions. So of course I could go here and put down a quick example. So I'll say, for example, let's suppose that I was interested in determining f of 0.5. Right? That means that I would want to know what is e to the 0.5 power. If I had no calculator, that's a tough question. But I notice that 0.5 is pretty darn close to 0. Maybe it's like right here. And so if I was to plug 0.5 into the line and then compare that to the y value that I would get out of the function, look at, like, they're almost exactly the same. So I can say that this would be roughly the same as going to the line and plugging in 0.5. which of course is really easy to compute. This is just 1.5. And the cool thing is I can actually go to a calculator to start to do some sorts of comparisons. I'm going to go to the calculator and actually see what is e to the 0.5 and how close was our guess. If I believe what the calculator tells me, then e to the 0.5 power is about 1.6. So, okay, we were a little bit off, we were a little bit low, and that's actually probably what we expect based on where the blue dot was compared to the black dot. Okay, so this is the idea of Calc 1. This is all Calc 1 problems. Note again, P of x only approximates f of x well for values that are close to 0. And it will do a very poor job of approximations if I pick x values that are far away from 0. Notice if I wanted to do like 10, then I would say, well, f of 10 would be e to the 10th power. But if I plug 10 into this line formula, I would get 11. And I can see that if I do e to the power 10, I am definitely nowhere close to 11. So the further away I get from plugging in 0, the worse and worse the approximation becomes. And I can see that as the gap between these two things continues to grow. Okay? So the question that we would like to ask is if there is any way to improve our ability to approximate. Can we refine the Calc 1 technique and make it into a new, more awesome and powerful Calc 2 technique? And one of the ways that we get to start onto that is by dealing with what we call a local quadratic approximation. And we'll tackle that in the next video.